Yeah.
Okay. Thanks everybody for coming to the seminar. It's a really great pleasure and also an honor for me to introduce Yann Brenier to the Einstein seminar. So he has a very interesting talk today, which I think appropriately honors the namesake of the seminar. He will be talking, the talk is from Euler's Hydrodynamics to Einstein's gravitation through Monge's optimal transport. Yann?
Wow.
Okay, thank you. Thank you very much. Thank you for the invitation.
Why don't we add Galois to that? Sorry.
Okay. Okay. I am stuck with, okay. I'm stuck with the first page now. What's wrong? Okay.
We see 5 lines.
Yes, and the title. Yes, perfect. Yes. So in the recent years, there have been some interest to link general relativity and optimal transport. In particular, Robert McCann actually has been very much interested in this link. And there is a paper already published by Roberts. And there is even more ambitious paper by Andrea Mondino and Stefan Zur, which is from 2018. I don't think it's yet published. And they have a formulation of the Einstein equation based on the definition of the Ricci curvature using the theory of John Lott and Cédric Villani on one side and Carl Theodor Sturm on the other side, which is, I don't know how much you are familiar with this. This is a so-called synthetic definition of Ricci curvature, and it's based on optimal transport ideas. Okay, and then Mondino and Zur have been able to modify that in a substantial way in order to be able to define the Einstein equation in these terms. So it's rather difficult, even for me to read that. Anyway, it's available. So I would recommend to look at that for you. But the approach I'm going to discuss today is quite different. And this is very much related to hydrodynamics and more precisely to the hydrodynamical formulation of optimal transportation theory, which was done by Benhamou and myself 20 years ago, and which has become quite popular actually. And the thing that I'm going to tell you about has been very recently accepted by the Compte Rendu Académie des Sciences 1 month ago, actually. And it's available also as a preprint. Okay, so let me do a kind of review of hydrodynamics from the mathematical viewpoint. And in my opinion, everything started in 1757, when Euler described fluids by PDEs. And so let me write the PDEs as we would do now I mean, this is the writing more like of continuum mechanics. Okay, it's not really the geometric way of writing it. So you have the evolution of the density field of the fluid and the velocity field of the fluid. So the density is rho and the velocity is v. So you have the continuity equation that tells you the evolution of the density and the momentum equation giving you the evolution of the density multiplied by the velocity, which is often called the momentum. And then you have the pressure field, which is in the paper of Euler, given function of rho. Actually, to be more precise, the paper of Euler contains both the compressible fluids equation and the incompressible fluid equation. So here I'm really talking about the compressible case where the pressure is a given function of the density. And this looks very simple. However, it is quite remarkable because in my opinion, this is really the first field theory in physics, because this is 1757. And the fact of, I mean, the idea of describing a complete physical model in terms of PDEs or evolution PDEs is really new at that time. And this is before Maxwell, Einstein, Schrödinger, and Dirac. So in some sense, or maybe are you arguing about that? Oh, sorry.
Yeah, no, I wanted to ask you, so this for the compressible one, this is a field theory, yes?
Yes.
But it's not so for the incompressible one.
Yeah, I bet. Yeah, okay. You could, well, I mean, yeah, well, yeah.
Well, I mean, what do you mean? Yes or no? I mean,
well, I mean, it's a little bit more obscure on the incompressible side because you have a constraint. But I would say that.
Oh, I see. If you add the constraint, it's still like a field theory with a constraint.
Yeah.
Oh, I see. Okay.
Yeah. But anyway, sometimes sometimes people think that in this paper Euler is only talking about incompressible fluids, which is wrong. Actually, it discussed both models. Yeah. Okay. Anyway, I think this contribution of Euler is remarkable from the physical viewpoint, but also from the mathematical viewpoint, because I think this is really the first multidimensional evolution PDEs ever written. So if you look at what was done before Euler, well, I mean, there is this, the one-dimensional wave equation was written by d'Alembert in 1746 in a very obscure fashion, actually. It's very hard to read. And there were some other equations like the divergence-free equation before, but I think this is the first time that really somebody has written a multi-dimensional evolution PDE and with modern notation. And also not only it is new, but it's also modern notation. And let me show you so this is of course a portrait of Euler. And this is the notation used by Euler. And you see that he calls U, V, W, the velocity field, T, X, Y, Z, the time and the position, P is the pressure already, and Q is the density that is usually denoted by rho now. But I mean, this is completely readable. And this is absolutely remarkable because as I told you before, if you go back 10 years before to the paper by d'Alembert, the notation are absolutely unreadable, even for the, so it's quite remarkable. And then you have on top, you have this famous continuity equation I mentioned before. And on the same page, you have also the possibility of considering the incompressible case with the famous divergence-free condition. Yeah. So you see, to reply to your question, I mean, in some sense, in the same page, you have the compressible and the incompressible case. Okay, so I think this paper is really readable. Actually, I put a link to this paper on my webpage if you're interested. It's very easy to find and it's very readable. Well, the only drawback, it's written in French, sorry, but there is also an English translation which is available in the same website. So I think you can get the English translation very easily. Okay, so now let me move to the least action principle, which is mentioned by Euler already in the paper. But what I'm going to tell you now, it's not explicitly written this way in the Euler paper. So it's not so clear in which sense Euler was talking about the least action principle. Anyway, in the more modern style, the least action principles tell you that to get the equation correctly, it is enough to look for fields depending on time and space, T and X, rho and V, density and velocity, which are critical points of this action functional, which is the space-time integral of rho V square over 2, which correspond to the kinetic energy of the fluid, minus phi of rho, which is the potential energy of the field of the fluid, and the potential function phi is related to the pressure function by this simple relationship. So you can, if you know P, you can compute phi and you get the action principle. Of course, when
you're assuming the equation of state.
Yeah, that's right. So this is the equation of state. And so it's true that in more modern fluid mechanics, so if you go to the 19th century, people understood that this model of Euler is too simple, so you have to use thermodynamics. And then in the modern writing, you would get an extra equation for the energy, and the function P will be a function of the density and the energy. So this is sometimes called the isentropic case, what really Euler did. But anyway, this is fine for my discussion. So I will not go to a more comprehensive description of compressible fluid with the more realistic thermodynamics. So here, the pressure is just a given function of the density. And there are critical points with respect to, let's say, compactly supported space-time, compactly supported perturbation, subject to the continuity equation. So you have to input this constraint on rho and v. Otherwise, you wouldn't get anything interesting. So you assume that rho and v are linked to each other by the continuity equation, that the time derivative of the density is balanced by the divergence of the momentum. So this is essential to the least action principle. And so after a little bit of calculus, you get the Euler equation correctly, with the little restriction that here the velocity field will be curl-free, no, just a potential velocity field. But it's a minor problem that you can fix by some other trick. Anyway, this is fine enough for me. And then just to give you an example of a state law of states. So if you take the isothermal case, the pressure is just a linear function of the density. And the scaling factor is the speed of sound, which is supposed to be constant here. So you have a constant speed of sound, C. The pressure is just proportional to the density. And the potential phi is like the Boltzmann entropy function, R log rho log rho. So this is an example. Okay, so this is enough for the least action principle for the Euler equation. So actually, I should emphasize that the least action principle here, it's a way of building the equation right. It's not a way to get the solutions. You know, it's not used as a tool to get solution to the equation. It's just a convenient way to get the equation right. And you know that least action principle have been used essentially in all field theory since. Okay, so this is a kind of universal trick in the mathematical physics. Okay, now let me focus on the degenerate case where the pressure is just zero. So this is a so-called pressureless gas, which is a little bit fantasy. I mean, but let's concentrate on this case for a while. So therefore, if you go back to the previous slides, so it means that you drop out the potential term, and you are just left with the kinetic term. And so you are looking for critical points of rho v squared over 2, where rho and v are subject to the continuity equation. Okay, so it's a kind of degenerate situation. And but the nice thing about this pressureless case is we get some convexity now. Why is it so? Because if you write this in terms not of rho and v, but in terms of rho and the momentum, which is rho multiplied by v, on one side, you see that rho v squared over 2 becomes m squared divided by 2 rho, because rho v squared is rho squared v squared divided by rho. So you get m squared divided by 2 rho. And you may know that the function of rho and m given by m squared divided by 2 rho is a convex function. And on the other side, the continuity equation becomes a linear equation because rho v is just m. So you get dt rho plus divergence m. So you have a linear constraint and a convex function. So which means that the critical points are really minimum. And the theory is much simpler. So then you can really use the least action principle for analysis. And in particular, it makes sense to minimize this quantity when you prescribe the density field at 2 given times. So for instance, the initial time 0 and the final time 1. So you can give the density field at time 0 and the density field at time 1, and you can minimize this action functional. And for the standard Euler equation with a non-trivial pressure, this wouldn't make a nicely well-posed problem. This is an ill-posed problem. So for the classical Euler equation, what is well-posed is the initial value problem, where you prescribe the density and the velocity at the initial time. So this is a different problem I am talking about now. And it turns out that it corresponds to this optimal transport problem introduced by Gaspard Monge in 1780 with the problem des déblais et des remblais. And you probably know that this optimal transport problem has become more and more important in many fields of mathematics. And there is a nice account of this theory in the book by Cédric Villani, and there is a more recent book more related to applied mathematics by Filippo Sant'Ambrogio.
Can you restate the reformulated problem?
So you mean this one? Sorry,
No, you said this, the reformulated problem can be treated with optimal transport. So what is it? How is it reformulated exactly? I mean, what's the change?
So then but I'm going to go to that in the next slide, actually. Yes.
Well, I haven't understood which problem you're talking about.
Okay. I think this will be clearer in the next slide. Yes.
Okay.
So, but just my last word about the propaganda for the field of optimal transport, that actually there has been application in any type of mathematics, so very applied one, data sciences, so it's in artificial intelligence, but also in number theory, more surprisingly, in the hierarchy of geometry. I saw a recent paper using this kind of idea in the hierarchy of geometry, So it's really, and of course, Riemannian geometry has been a big target of optimal transport in the recent years. The Riemannian geometry, yes. And I mentioned this result by John Lott, Cédric Villani, and Carl Theodor Sturm about a new formulation of the Ricci curvature, for instance.
Yeah.
Okay. And there are many connections with probability and statistics, of course. Also. Okay, so now this is a nice portrait of Gaspard Monge. I think this is the nicest one I found. And let me tell you the definition of the optimal transport problem in the style of Monge, more or less as Monge stated it in 1780. So the problem is the following. So you have two density fields, rho 0 and rho 1. So they are depending only on the space variable. They are given to you, and they are normalized. That is, the total mass of rho 0 and the total mass of rho 1 should be equal. Otherwise, the problem doesn't make sense. And you try to find a map, let's say a Borel map in modern terms, that is transporting rho 0 to rho 1 in the sense that the measure rho 0 x dx, the measure rho 1 of y dy is the image or the push forward, if you prefer, of rho 0 x dx by the map T. So T is mapping x to y, and you transport rho 0 to rho 1 like this. And now you try to see what is the best map in the sense that it's as close as possible to the identity map. So, I mean, if rho 0 and rho 1 are equal, of course, you can take the identity map. And then you get a cos 0. If rho 0 and rho 1 are different, you don't know. So this infimum is not necessarily 0. Usually it's not. And this is what I call Monge sub 2 squared. So now, actually, to be absolutely precise, what Monge did in 1780 was the case where 2 is substituted for by 1. So it's the L1 equivalent of this. So this is really the Monge problem. However, it turns out that you can do that for any exponent p between 1 and plus infinity. And the case p equal 2 is particularly interesting. And I think most of the applications are related to the case of the square. So in some sense, you don't minimize the distance, but you minimize the distance squared between the initial point x and the target point t of x. That's a Monge problem, as it was stated in 1780. But what is the connection with Euler? The connection with Euler is that you can show that actually you can reformulate this number in terms of fluid mechanics, just as I did in the previous slides. So actually, it turns out that this number is the same as when you minimize the space-time integral of rho v square, where rho and v are the field, the density and the velocity field of a fluid moving rho 0, the density field rho 0 to rho 1, between time 0 and time 1. And this is exactly the problem I discussed before, if you remember. This was exactly the problem I came up with by considering the Euler equation in the degenerate case where there is no pressure. So in some sense, you can rephrase the problem of Monge in the vocabulary of Euler. And this what which we did with Jean-David Benamou 20 years ago. And actually, this formulation of the optimal transport problem is really useful, and often many generalizations of optimal transport problem are based on this formula, not on the first.
So I want to clarify. So with this modified version of Euler, pressure 0, then any solution of Euler will, when you rewrite it this way, you'll see that it realizes the infimum. And conversely, anything that realizes the infimum this way is a solution of Euler.
It's a little bit more subtle than that, because if you run the initial value problem, you may have some focusing. I mean, at the level of the fluid particle, it just means that the fluid particle have no acceleration. So they move along straight lines. And therefore, for the pressureless Euler, you have this problem of the focusing, the possible focusing of these rays. Because as you know,
yes.
I mean, rays are very,
yes.
Yeah. And therefore, you can get singularity in finite time.
Yes.
Okay. Now, if you address the minimization problem, where you don't prescribe the initial velocity, this is a nicer problem. So in some sense, then you avoid the crossing of the rays automatically out of the minimization principle. So in some sense, there is a discrepancy between the initial value problem and the minimization problem. So what you said is not exactly correct. But
what is the correct statement?
One part is fine. One part is fine. So if you have a minimizer, then you get a solution of the pressureless Euler equation. Yeah, that's correct. Yeah.
A Borel solution.
Yeah, I mean, of course, I'm not talking about the smoothness of the, of course.
No,
yeah.
but I want to know the statement.
There is a lot of analytical issues
we can have
about how smooth are the things. Yes. Yeah,
no,
sure.
okay. You're saying the pressureless equation makes sense for a solution, a Borel regular thing to be a solution, and it's exactly the optimal transport path. Between each pair of times, it solves the optimal transport.
Yeah. Yeah.
And
there is also a restriction.
No, I want to know the other half, though. That's, you see, if it's Monge, then it's Euler. And then if it's Euler, then it's Monge. I want to know two statements.
Yeah, but I think this Euler is richer, it's more subtle than the Monge in some sense. So you can see Monge as is more complicated, because for the Euler equation, you are interested in the initial value problem.
No, I'm not interested in initial value problem. You can make a statement anyway. I mean, you know, you have a path.
So otherwise, it's more or less equivalent, but it's just a matter of functional spaces and functional analysis to decide which space you are working with.
No, but without those nuances, what's the English sentence that relates optimization and this modified Euler equation? What's the act? I don't have the sentence yet.
Okay, so now
you haven't committed yourself to a precise sentence.
Yeah, so in some sense, my attempt was to show, to present the Euler equation from the least action principle viewpoint. And now I'm telling you that when there is no pressure, I mean, the least action principle can be used as a minimization, space-time minimization problem, where you prescribe the density at the initial and the final time. And then by that, you are just collapsing to the Monge problem. So it's a kind of lift of the Monge problem in some sense.
Yeah, but could you?
The Monge problem is
no, but wait a minute, Yann. Come on, just say this. You know, qu'est-ce que c'est l'énoncé?
Ah, so the énoncé is written here. So I gave a definition. So the first line is a definition. It's a definition of what is the Monge distance squared.
No, okay, I have it, but I mean,
and
I
now
understand these formulas.
The theorem tells you that you can write that this way.
What?
And the theorem tells you that this definition coincide with what you would get from the least action principle from the pressureless Euler model. Is it
No,
clear
but
enough
I
or
mean,
not?
but if you have a family of Monge things for every pair of times, do you get a family of optimal transport maps that satisfy the pressureless Euler equation in some weak sense?
Yeah, that's right. So you could, for instance, if in the second definition, you get the history in time between rho 0 and rho 1. And therefore, you can reduce you can look at a smaller time interval, T0, T1, and you would recover by looking at the problem on the shorter time interval to the Monge problem with the corresponding density. So there is a kind of, you can localize that if you want. Yeah. Is it what you
No, okay, I'm going to say a sentence and you just answer yes or no, okay?
Okay.
Suppose on some time interval, for every pair of little times, you have a family of T's, capital T's, that satisfy the Monge minimization for every pair of little T's. You have a family of measures and T's transporting and so on, every pair of times, okay? And satisfying the optimal transport locally all along in the interval for every pair of times. Then, does that family of T's satisfy a modified Euler equation in the Lagrangian sense?
Yeah, I would say yes.
What? Yes?
Yes.
Okay. And conversely, suppose you have family of T's that satisfies Euler in the pressureless sense. Will it, for every pair of T's, satisfy the optimal transport?
Yeah, you have to, then you have to put the additional condition in the other way around. Yes. It's not, so it's not complete, it's conditionally true, what you said.
So Monge implies Euler, but not Euler implies Monge.
Yeah, in some sense, yes. Yeah.
Well, no, yes or no. I mean,
yes.
I mean, for Borel functions. So does the equation make sense and do the statements make sense? And then are they true? Because you have to use all pairs of times to try. Okay, that's what I'm suggesting. Use all pairs of times. I wrote you about that once, 10 years
it's consistent with this. Yes.
Well, but okay, well, all right. I stopped talking under protest.
Okay, anyway. So now, okay. So now, I mean, for the rest of the talk, for me, optimal transportation will be this, the second statement. So I will completely forget about the original definition of Monge. So for me, optimal transport is just this minimization problem where the structure is you minimize rho v square subject to dt rho plus divergence of rho v is 0. And what we are going to discuss now are generalization of that. Okay.
Well, let me try to read, but I see. So the previous discussion sort of says the Monge condition is actually better than the Euler condition because Monge implies Euler, but not Euler implies Lagrange. So this is very interesting for us. So he's saying there are these optimal transport conditions that are better than just the Euler equation itself.
Yeah, and well, I mean, you get some additional features, yes, because you get the no recrossing condition, and also you get a curl-free fluid. There is no vorticity. No vorticity.
Get a what free?
A curl-free, no vorticity. So V will be the gradient of something. It's a potential flow.
No vorticity, is that what you said?
No vorticity.
Okay.
So it's more restrictive. Yeah, in some sense, you agree it is more restrictive than the Euler. So in my opinion, this means that the Euler model is richer.
Okay.
And also, I mean, I'm just talking about pressureless Euler. But of course, if you are discussing with the true model of Euler with the pressure, then it's much more complicated than the optimal transport. Yeah. Anyway, optimal transport is a tool nowadays. It's more like a tool. Okay, so maybe I'm just actually answering a little bit your question because this minimization problem, the optimality equations are written here, and you see that the velocity is automatically the gradient of some potential phi. And therefore, it turns out that you can rewrite the Euler equation in a simpler way because of that property, just as the dTV is just the gradient of v squared over 2. So you can, I don't know how much you are familiar with the terminology of Burger's equation. So you can see that as a multidimensional inviscid version of the Burger's equation. So it's simpler. In some sense, the structure is more precise than in the Euler case. So maybe it's a way of answering your question again. Yes.
When you say multi-dimensional, you mean infinite dimensional?
Yeah, it's multi-dimensional. Yes, yes.
Well, what do you mean by multi-dimensional? What dimensional?
Because the V is a vector valued function. So X and V belongs to RD. So maybe I should have said that. Yeah, I think RD. So you are in D-dimensional space. And so you have D space coordinates. And the V is a vector value. It's a tangent vector. So if you would work on the Riemannian manifold, so this would be a Riemannian manifold of dimension D, and V will belong to the tangent space. Okay.
Okay.
Actually, there is a nice theory of this Monge problem, in the setting of Riemannian manifold, which was done by Robert McCann in the early 2000. Yeah, there is a nice paper on the Riemannian setting if you're interested in that. Okay, so now let me do a proposal. At the moment, it's just a proposal. I want to do a kind of extension of this minimization problem, or this critical action problem. And I'm going to tell you that this is related to general relativity. So the setting is the following. So we look for fields of 4x4 real matrices, which are defined on what I call the phase space, xi in R8. So X is the space-time of gravitation, so 4 dimensions, space and time. And Xi is a tangent space, so it's R4 times R4. And therefore, we get 8 dimensions. And these fields, C and V, are fields of 4x4 real matrices. Okay, now we are looking for critical points of the trace, the integral on the phase space of the trace of C times V squared. So this is the multiplication of matrices in the usual way. So C times V squared is just a square matrix, 4x4. You take the trace and you integrate that over X and Xi. And then you look at critical points subject to what I call the generalized continuity equation, which is very similar to what we had before, but it's a little bit more complicated here. So you get, here I use the convention of relativity that repeated indices are automatically sum up. So J here is repeated, and they should be up and down. So up and down indices are automatically summed up. So then I get the first term, which can be seen as the X divergence of C plus the Xi divergence of CV plus VC is 0. So CV plus VC, of course, is a matrix. Actually, it's a symmetric 4x4 matrix, and C is also a matrix, and so everything makes sense. So this is what I call a generalized continuity equation. And now I have to input some additional constraint, but these constraints are more or less symmetry constraints, and they are okay. They look horrible, but this is just they are just linear differential constraints in the Xi variable. So the first one, for instance, dxi vkj is equal to dxi j vki, just mean that vki actually is the gradient in Xi of something, okay? And the other condition is of the same type, except that you have to do a little bit of manipulation with the Kronecker symbol. So it's a little bit more messy, but it's a little bit messier, but it's a similar condition. So that's my kind of generalized optimal transport problem. It's a matrix valued optimal transport problem. But you see that the structure is essentially the same as the one we had before. Before we had, instead of the trace, we had just the density field multiplied by the square of the velocity. And you had the time derivative of the density was balanced by the x derivative of the density multiplied by the velocity. But it's more or less the same, right? It's just.
Which is time?
Sorry?
Which index is time? Oh, you made an analogy. Sorry. Okay.
Yeah, that's right. So now, in some sense, the space-time variable x plays a role of time, and the dual variable, which is also in R4, plays the role of the space variable. Otherwise, the structure is almost the same. And so now I have the theorem is the following. And this is concerning general relativity. So you take a solution G gamma of the Einstein equation in vacuum. So what do I mean by smooth solution to Einstein equation? So G is a notation for the metric, and gamma is a notation for the Christoffel symbol, describing, I mean, the connection attached, the Levi-Civita connection attached to the metric G. Okay. So, and I guess you know that the Christoffel symbol can be computed out of the metric. This looks like essentially like, how would you call that? A logarithmic derivative of the metric. It's more or less like dj divided by g in some sense. Okay. And now I define my matrix, my field of matrices capital V, just by applying the Christoffel symbol. So the Christoffel symbol is a function of space-time. So in my notation, X is a space-time. And I apply that in a linear fashion to psi. So which means that this is a linear function of the dual variable psi. Now I define the other field of matrices, is capital C, as a kind of derivative of some potential capital A. So you see, it's not exactly the derivative because I have to remove a term involving the Kronecker symbol, and this is why I had this slightly complicated constraint in the previous slide. And now the important thing is to define this potential capital A, this vector potential capital A. So the vector potential is just the variable psi multiplied by the determinant of the metric. So the metric is a 4x4 matrix. So you can compute the determinants. And then you take the cosine of the quadratic form associated to the metric, applied to a tangent vector psi. So G alpha beta is a metric, it depends on space-time, and it's applied to the vector psi twice, psi alpha, psi beta. So this gives me a scalar function, and then I take the cosine of this, and this is the definition. And so now the claim is that this field C and V are solving the matrix valued optimal problem that I proposed before. So there are critical points of this generalization of the kinetic energy subject to the generalized continuity equation. So that's
now you have three things, V, C, and A.
Yes. And before we had only V and C. So, but C is actually, it's a little bit like in electromagnetism where you have the vector potential and the electromagnetic field. So A plays a role of a vector potential, and out of A, you can compute C. And you can notice that capital V depends only on the Christoffel symbol. It doesn't depend directly on the metric. And conversely, capital A depends only on the metric and no on the derivative of the metric. So there is a clear separation of A and capital V. But of course, ultimately in the Einstein equation, gamma is really depending on G, because this is like a derivative of G, a logarithmic derivative. But the statement is, I think, is quite simple. So you do this. So the most mysterious formula is the formula for A. I will try to explain why it comes up. Yeah, and so this recent paper is just a way of justifying this statement. So there is no analysis, it's just a matter of computation. It's just a way of checking that the Einstein equation are really linked to this matrix valued optimal transport problem.
Which is also linked to the pressureless Euler equation.
Yeah, I mean, the pressureless is become like a toy model in some sense. It's like a simplified version of that, but highly simplified. Okay.
So Euler, I mean, so Einstein's equations in matrix form, I mean, Einstein's equations in actual form is like the simplified Euler without the pressure in some matrix form.
Yeah, that's right. In some sense, yes.
You sort of have to replace the fluid by a little 4x4 matrix.
Yeah, that's right. That's right. That's right. So, which is I mean, you know this comment, which was already given by Laplace, that he said at that time that, everything is in Euler. Of course, there have been more modern mathematics after that, after Laplace. But at the time of Laplace, he said, well, I mean, you should read Euler because everything is in Euler. So it's almost a claim that even the ancient equation is more or less kind of generalization of the work.
I've read a quote of Euler where he says, and he uses this word, he says, analysis is not yet sufficiently developed to understand these equations.
Actually,
Euler said that.
I have this slide on the previous version of this file, but okay. I just removed it this morning. And there was the statement in French, and is explicitly mentioning this about the Euler equation for fluids. He said that it's absolutely fascinating because he said that everything concerning fluids is explained in my equations, which is actually wrong, because of course we know that there is more sophisticated model with compressible Euler, Navier-Stokes, and blah, blah, blah. But at least he said everything from the physical side is in my paper. And what is missing is the analysis, because the analysis is not yet enough developed to address this equation.
Exactly. Yeah.
And it's fascinating because 250 years later, the Euler equation is still one of the massive problems in PDEs.
Yeah.
Okay, together with Navier-Stokes, of course. So actually, I'm sorry I dropped this slide at the last moment because it's amazing actually. So, just I was mentioning that you see in this formula you have a cosine, but of course everybody knows that the cosine is the real part of the exponential. And of course, if you put the exponential, it means that this formula looks like an imaginary Gaussian. So it's e to the I g alpha beta c alpha c beta. So it's a kind of imaginary Gaussian. And I have the feeling, but this I don't understand at the moment. I have the feeling that this should show some connection with something else. The fact that you have a kind of Gaussian popping up in this formula is really mysterious to me, and maybe deserves some further study. Anyway,
quantum theory, right?
But
quantum theory.
Yeah, it could be also linked with quantum theory, also something like that. So, okay, I just put the stamp of Euler again because you can see on the top the formula e to the I phi cosine plus I sine phi, which is due to Euler. And then this is a way to review the fact that the cosine is the real part of the exponential. Okay, so. Okay, so now let me make this to emphasize this dictionary between the Monge and Einstein via Euler. So in the Euler and the Monge theory, you have the space-time Tx, and in the Einstein business, X becomes a space-time, and then you need the dual variable, the tangent variable psi. The tangent bundle of the space. And the scalar density rho becomes the vector value, the density C. Now the continuity equation, which was written by Euler like this with the density rho and the velocity V, it becomes this of a matrix version of the continuity equation. And this kinetic energy term becomes, it's a very natural generalization, the trace of CV squared. So it looks almost the same. Okay. And also something that I found amusing, that this matrix valued formulation of the general relativity in vacuum sounds a little bit like classical continuum mechanics. So it looks like a 19th century type of physics and mathematics. And you don't see, actually, for some reason, you don't see really the Lorentzian geometry anymore, which you can, I mean, could be considered positively or negatively, depending on your taste.
Well, can I make a comment on that?
Sure.
When you look at 3x3 matrices, right?
Yes.
Then there's a natural trace inner product on the Lie algebra, which is invariant. So the Lie algebra acts on itself and it keeps Lorentzian geometry invariant. And I think with 4x4, there's something, I mean, you see in the Lie algebra, you have Lorentzian geometry. So it's conceivable that it's sort of there anyway, even if you don't see it explicitly.
Yeah. No, but you know, I like the concept of alien mathematics. So the fact that in some maybe you could have started, you know, general relativity in the wrong way. So then after that, what I mean, discovering Lorentzian geometry would be kind of a later issue, right?
Right.
You know. So I think, yeah, mathematics can be done in a different order, you know, depending.
I see.
It depends on the history, actually. It's just for historical reason. Okay. Now something which, I mean, this is not in the paper, but this is a calculation I made recently, that you can also do a similar thing for the free Schrödinger equation. So of course, the free Schrödinger equation is not a big deal. It's a linear equation, so it's very simple. And there is
which equation?
The Schrödinger,
the
quantum mechanics equation. Schrödinger
equation. Oh yeah.
Schrödinger. Erwin Schrödinger.
Okay.
Can you see that on the screen?
Yeah, it's there, but I can't read.
Okay. So it's a little bit complicated, the formulation of the Schrödinger equation, a little bit weird, and it's based on the hydrodynamical formulation of the Schrödinger equation, which was designed a long time ago by Madelung, actually 1 year. I mean, at that time, it's amazing because Schrödinger, I think, wrote the Schrödinger equation in 1925, and the paper of Madelung was published 1 year later. And so he proposed a kind of a hydrodynamical version of the Schrödinger equation. And based on that, you can reformulate the Schrödinger equation in the following way, which is a little bit, it's very weird, but you will see that the structure is almost the same as the previous one. So we look for complex fields, C, V1, Vd. So you have the space-time, the space dimension is D. So you have C and D other complex fields, and you are looking at critical points of the real part of CVK square. I mean, I sum up with respect to K, and this is subject to this complex version and dispersive version of the continuity equation. So it looks like the continuity equation we saw before. I mean, it's exactly the same as for Euler, except that now you have complex fields. And on top of that, you have this dispersive term, I time the Laplacian of C, which of course is the input of quantum mechanics in the field, in the business. But anyway, you can see that the Schrödinger equation has a very similar structure also. So in some sense, I try to put in the same package the Euler equation, the Monge equation, the Einstein equation, and the Schrödinger equation. Sorry.
It's good. That's good.
Yeah. And of course, the mysterious thing is maybe it's very tempting now to say, well, I mean, this is an additional term. I mean, which was not in the previous case. So maybe
imaginary viscosity.
Yeah, that's right. And of course, I mean, the Schrodinger equation, the linear Schrodinger equation is just the linear part of this equation. So it's a kind of very absurd formulation of the Schrodinger equation in a very nonlinear way. However, the good thing is it allows you to put that in the same kind of framework as the two previous theories. And I find that quite interesting.
So the optimal transport. No, the optimal transport can be used to study this equation.
Yes, that's true. Yeah, that's correct. And also there is okay, maybe this will be going a little bit too far, but you can do a real version of this problem by taking C and Vk to be real valued function, and you drop the I and you put a -1. So you really get the heat equation. Yeah. And this is a well-documented problem because this is a so-called Schrödinger problem, not the Schrödinger equation. It's another work done by Schrödinger in the 1930s about, it's more related to statistical mechanics. And this Schrödinger problem is a kind of a stochastic generalization of the optimal transport problem. It's a very fashionable problem, actually. It's very useful for many applications. And the only difference with this one is the fact that you do this, take the real valued version of that, and you replace the dispersive equation by the heat equation. So you get minus Laplacian of C. And this is very well documented. However, the genuine Schrödinger equation, the one of quantum mechanics, can be written in this style using complex valued functions. And I'm pretty sure, and I don't know at which points Schrödinger was aware of that. So he could have understood, because he contributed to the two different stuff. I mean, the Schrödinger equation and the Schrödinger problem, and there are a lot of similarities, obviously. Anyway, so now let me tell you a little bit about how you can prove this result. So I'm concentrating on the theorem about the Einstein equation in vacuum. And so in my opinion, it is very fruitful. Maybe if it is not so, I mean, I don't see it, it's not so often written, or maybe I never saw that written this way, but maybe it is written in a equivalent way in a different wording. But anyway, I think it's very fruitful to look at the equation in this phase space, introducing this psi, this tangent variable psi, and you get the definition of capital V this way. And the good thing about this writing is that you can rewrite the Riemann and the Ricci curvature in a rather efficient way. So at least for me, because I'm not a geometer, so it's really hard for me to remember the formula of the Riemann curvature. It's quite complicated. However, if I do this kind of lifting of the Christoffel symbol to the phase space, then everything becomes much simpler, because you recover the fact that, I mean, ultimately we know that the Riemann curvature is a kind of commutator, but here it's very clear. So we just consider this field of matrices as a collection of 4 vector fields. So the vector field will be with component Vj, and K will be the index of the 4 different vector fields. And now, if you write that this way, you can see that the Riemann curvature tensor applied to this tangent vector psi is nothing but a kind of commutator between the derivative of Vj in the direction of Vk and the derivative of Vk in the direction of Vj. So it's really easy to remember this formula. And I must say that I know this trick for some years ago. And this is the way, if I want to recover the formula of the Riemann curvature, I will do that. So it's a very simple thing to do. So now the next step is that, you know, this formula is a combination of products of the V and the derivative of V. However, we can put every derivative outside like this, in what the PDE people call a conservative form. In conservative form, so you put the derivative outside of V, and this is possible because in the Einstein theory, the connection is torsion-free. And torsion-free means that this Christopher symbol is a symmetric function of little k and little gamma. So you can exchange k and gamma without affecting the Christopher symbol. And out of that, you deduce, you can write this formula in conservation form. And most of the PD people love this kind of conservation form because you can use, in some sense, distribution theory much easier, in a much easier way, because you can multiply by a test function and you can integrate by parts. So it's a nice way of writing the Riemann curvature. And of course, in the Einstein theory is about the Ricci curvature. And the Ricci curvature is a contraction of the Riemann curvature when you contract the indices n and j. And therefore, you get, by contraction, you get this very simple formula for the Ricci tensor. Okay, it's just the previous one where you are just contracted n and j. This one is harder to remember, I would say, because of this contraction. The structure is a little bit messed up. But anyway, we have a nice formula for the Ricci curvature. Now, if you look at the definition of the Einstein equation in vacuum, Einstein equation in vacuum is just a way of saying that the metric has a zero Ricci curvature. So in some sense, we can encode the fact that the Ricci curvature is zero, which is the characteristic of Einstein equation in vacuum, by saying that this quantity is zero. This quantity is zero. So, and this is what I call a zero Ricci curvature phase space equation. And this looks like just a matrix valued version of the Burger's equation I mentioned before. You see that the structure is pretty much the same. So now X plays a role of T. So you have a linear derivative in V. In X, the linear derivative, and you have a derivative in psi, which plays the role of the space variable before for the square. So it's more or less a generalization of that. Okay. So this is the point. And okay.
Okay.
And now, okay, sorry, I'm going backward. So now what I can do is, so I don't know how much time, because then I can enter a kind of semi-proof that might be a little bit boring. So I don't know how much time is acceptable for you.
There's still 20 minutes left in the seminar.
Okay, so let me try to be as light as possible for this part. So the idea is to play a trick with the simple Burger's equation, and then you have to admit the idea that this can be generalized to the Einstein equation. And then, therefore, I will not talk about the Einstein equation anymore. I will play this game with this simpler equation. And for this simpler equation, you will see that everything is quite elementary. It's very elementary, actually.
Could I just ask, in
Sure.
that reformulation of the Ricci flat, I mean, can you see these exact solutions like Minkowski space and Schwarzschild? And I mean,
actually, there is something that I don't master completely because I am not an expert of general relativity. So I did not check a lot of things, but there is something a little bit striking here, that this equation is only involving the connection. Right, if you remember that V ultimately is related to the connection, and therefore it looks like incomplete to describe general relativity, because in general relativity you have also to tell that gamma is a Levi-Civita connection for some metric, and this looks out of that because connections are not necessarily Levi-Civita connection, right? So this equation is not satisfactory. However, we are going to see that in the same way, for the optimal transport equation, a problem, we had this equation, but in this equation, there is no rho. There is no density in this equation. And so I am going to tell you on the model, on this toy model, how the density field is emerging from this equation. And what is happening for the Einstein equation is the same. So the metric will be emerging from this equation. And that's a little bit strange, but I don't fully master. Maybe it's related to the boundary condition that I never talked about, that you have to add to this problem in order to solve, for instance, the initial value problem. But at the moment, at the level of equation, the equation relating V to the metric will emerge from the strategy I'm going to follow now. And I will show you that on the simple model of this equation. So I claim that out of this equation that we found as an optimality equation for the optimal transport problem, we can recover the optimal transport problem. So this single equation is sufficient to recover the full problem. And that's what I'm going to tell you about now. So the first step is to look at this equation a little bit like the analysts do when they do the weak formulation of an equation. So you know the trick, you multiply the equation by a smooth test function and you integrate by parts, and you integrate. So this is what is written here. So if I multiply by a test function, which will be a vector valued function A, because V is itself vector valued. So I multiply that by the scalar inner product, and I integrate by parts. So I get minus dtAV out of the multiplication by A, the integration by parts. And for the gradient of V square over 2, I get by duality minus the divergence of A, because A is a vector valued function, times V square over 2. So I hope the notation are more or less okay for you. I mean, this is a questionable notation taken from more like continuum mechanics style. Okay, so now you consider this as, you consider the critical points of this functional involving both the V and the A. So that's a key idea at the moment. So now, if I look at critical points, it means that I have to differentiate this expression with respect to both A and V. So if I do that with respect to A, of course, I recover the original equation because this is like the weak formulation. So if I differentiate this expression with respect to A, I will go back to the original equation, at least in weak form. Okay, this is what I call equation 1. But so there's nothing, I mean, completely expected. However, if I differentiate with respect to V, I get something of some interest. If I differentiate with respect to V, I get an equation for A, which is very easy to get. You get, okay, you just differentiate, you know, you can differentiate pointwise. There is no integration by part to do. So you get just minus dtA minus the divergence, minus V times the divergence of A 0, which is written the equation 2. So out of the, if you look at critical point of this, this action, you get 2 equations now. So this is what I call it. So in some sense, the second equation is emerging from the previous one. So of course, it has a triangular structure because V is as its equation for itself, and A is depending on V. It's a linear equation for A depending on V. So it's a kind of triangular structure. Okay. Now, the idea, which is a little bit weird, but this is, I mean, related to Legendre transform you do when you do going from Lagrangian mechanics to Hamiltonian mechanics is more or less the same. So now the idea is you substitute for dTA in the functional the value given by the second equation. So, I mean, it's trivial to do. So instead of minus dTA of V, you will get V dot V divergence of A. Therefore, you get V square divergence of A, which partly compensate the minus 1/2. And at the end of the day, which is very short, so you just get this expression. So you get a kind of a new version of the action, which is I sub 2, and which is given by this formula. And now I claim, that's a very simple claim, that whenever AV is a critical point for the original action that I wrote before, then AV is also a critical point for this modified action, I sub 2, but subject to this constraint. And then there is, okay, so I think maybe I will skip that because this is But it's very elementary, and I tell you that the proof is really contained in this formula. So it's very short proof. So it's very easy to see that by doing this substitution, you are not doing stupid things. You are just getting a new characterization of the pair AV in terms of the reduced action I sub 2 rather than the original one. And then you have the proof here. So maybe I skip the proof of that. Okay, so now let me, yeah. Okay, so is it okay if I skip that? Because maybe I think time is too already quite long. So now the final idea, we reformulate this problem in terms not of A and V, but on the divergence of A and V. Why is it so? Because you see that the equation 2, actually, you can really get rid of this potential vector A, because if you take the divergence of that, you get the dt of the divergence of A plus the divergence of V times the divergence of A0, which in terms of rho is just dt rho plus divergence of rho V. So we get the continuity equation. So here, and if you do the same for I sub 2, well, I mean, you just get rho V squared over 2. So which means that if you start with this multidimensional Burgers equation, you have never heard in your life of what is a density field. You never heard about the continuity equation, and automatically you get them. So the continuity equation and the density field are emerging from the equation, the Burgers equation. And this is a really strange property. And therefore, of course, here we recognize the optimal transport problem written in the hydrodynamical formulation, which amounts, I remind you that it amounts to minimize this quantity subject to this continuity equation. So now you have the scheme for the elementary case of the multi-D Burgers equation. And now the complete proof of the theorem about Einstein equation is just to do more or less the same strategy, but you start from the zero Ricci curvature equation. So let me just go back to the zero Ricci curvature equation. So you do that. You introduce you introduce a test function for that. You introduce an action for that. You reorganize the derivative in a funny way, as we did, and then you get the more or less the theorem. And okay. So I think at least I gave you a flavor of the strategy that you can use. And to get the Schrödinger formulation also, you can do exactly the same trick. So it works in the three cases. And I think that's all.
Okay.
Thank you for your attention.
Thanks very much, Yann, for a very, very beautiful talk. There are a lot of comments and questions already. Are there any others?
Oh, you said there are a lot of questions and comments?
There were already a lot, but are there more?
Well, I always have another question.
I had one. Yann,
go ahead.
so, okay, thanks. When you had a derivation for the optimal transport representation of the Schrödinger equations,
yes,
was there any understanding from those kinds of calculations of how to possibly derive other equations with different linear parts, like for example, different skew symmetric linear operator like KdV?
Yeah, of course. I mean, I didn't try to look at, for instance, for the Einstein equation. It would be very appealing to use a kind of a Dirac operator, you know, like a first order things. Yes, but I don't know. For instance, I don't know if I can do the same trick for the Dirac equation, for instance, the Dirac equation and of course, I mean, this is a tempting game for the Einstein equation themselves, but I didn't try that yet. Yes. But that could be, yeah, I think that's very natural to do that, but it might lead to nowhere. Yeah. But who knows? Yeah, maybe it's a good idea. Yeah. But probably the first thing would be, I mean, the thing that I have not been able to do so far, it's to try to put the Dirac equation, which is really the quantum mechanics equation, which is compatible with special relativity in this framework. And so far, I don't know how to do it. And it's particularly because there is no this Madlung transform that I discussed without explaining it. In my opinion, it is not known or not mastered, at least for the Dirac equation. So there are some paper in the theoretical physics literature on the Madlung transform for the Dirac equation, but it's very few. There are essentially one authors who try that, and this is not so clear to me, at least. But I think it would be really nice to put the Dirac equation in this framework, in this business. So yeah. And okay, so you could say the same for Maxwell, but yeah, I mean, this is, I was thinking about the beautiful nonlinear version of Maxwell equation by Born and Infeld, which I really like very much, but I was not able to get anything interesting at the moment out of Born and Infeld. Yeah. So, yeah.
So
it's an interesting point of view, though. Yeah.
So getting back to general relativity.
Yes.
So you have these connections between general relativity and Euler. Yeah.
In general relativity in vacuum. I didn't
in the
really
vacuum,
address
yeah,
the full
right.
equation.
Right. But so this is really perhaps in an orthogonal direction to your talk, but I mean, just the words seem like it might be related. I've always, you know, if you spread a fluid out in space and then that's the matter field of Einstein's equation, and then it starts moving, there's supposed to be, or some aspect of that is supposed to be like the fluid equations.
Yes.
But I don't understand the statement. And so do you know, can you say the statement? Or is it, and then the real question is, does what you're doing help you understand that statement?
No, I mean, because I mean, this is a kind of generalization that can be not really put, strictly speaking, in the framework of fluid mechanics, right? So I don't know any classical continuum mechanics model like that. So I don't know if I'm answering your question, actually.
Okay.
Maybe I'm not. Sorry.
Well, does anybody in this seminar know this? Even if you spread a medium around and you somehow look at some aspect of general relativity, you get something related to the fluid equation.
Well, actually, what is pretty well documented is the coupling. I mean, you have a fluid in a general relativity setting. Yeah, that's quite well documented. So you know, you have the right-hand side is the energy momentum tensor, and you can build that out of some fluid models. And this is like the complete Einstein equation for self-gravitating fluids. So this is well documented. This is well established, actually.
Can you say the statement again, please? I didn't.
Okay, that is you are describing the general relativity for a self-gravitating fluid. So
what's the adjective set?
Yeah, you can write the coupling between Euler and the Einstein equation. Yes, that's quite common, actually, to do that.
But what's the statement?
The statement is this is a kind of combination of fluid mechanics and Einstein equation. But of course, it's not at all the idea which I try to share with you today, because this looks like something else. So maybe there is a way of understanding that as a coupling between fluid and gravitation, but it's more like a general. In my opinion, it seems to me that this Einstein equation looks more like a generalized version of fluid mechanics.
I think, Dennis, you might be thinking.
Level, it's interesting to look at the discrete level, you know, like in the simplices and this kind of things, to understand that this way also.
So you might be thinking
of discrete models. Yeah, this might be useful to understand the link, actually. Maybe to I think you've been involved very much in the discrete fluid mechanics, And maybe by looking at a discrete version in space of this kind of generalized optimal transport problem, maybe there would be some interesting thing to understand. Yes, yeah, could be. Yeah, yeah. That's I have not thought about that before, but maybe it's a good idea to do that. Yes.
Theo, what were you going to say?
I think you might be thinking of this correspondence between a fluid theory on the boundary, like a horizon of a black hole,
I
and
see.
gravity in the bulk.
Yes.
So there, yeah, in the physics literature, there's something called the fluid gravity correspondence, and there's also called, I mean, there's a couple of different things that have different names all related, and it doesn't have to do with a fluid matter model, but rather it's some geometric aspect of a solution of Einstein equation, maybe vacuum, where a lower dimensional, some hypersurface has a property which is fluid-like. And
Yeah, I see.
I don't know the precise statement or whether there really is a precise statement, but
yeah,
that might
actually,
be what you're thinking.
yeah, I've seen this kind of paper. Yeah. So, but I don't master that. The only thing I can tell you that I discussed about this model with a specialist of quantum gravity and Bernard Julia, actually, and at least he didn't see a direct connection with these kind of things. Yes, because otherwise he would have told me. But at least he. But I vaguely know this. What you mentioned, that of course I don't master at all this kind of papers. These are too difficult for me. Yes. But also this was, maybe it's related, to this possible interpretation of Einstein equation as a kind of thermodynamical equation also. I don't know. I don't know how much you are familiar with this. This is related to what you said, I think.
Okay. Thank you.
Well, Yann, thank you very much again. It's 1 o'clock. We made it to the end of the seminar. Thanks everybody for coming. Yann, thank you again for accepting our invitation, giving a very beautiful talk.
Yeah.
And
Bye-bye.
have a good day, everybody. Take care.
Thank you.